This lecture is going to be a fun one. We're going to go outside and we're going to look at the universe, virtually anyway. We're going to stay inside and look at your DVD, I hope. But we're going to take a look at what the universe looks like on the largest scales, and we're going to get good news. The universe looks pretty much the same everywhere. It's a dramatic, simplifying feature that our observable universe seems to have. So in fact, this lecture is going to cover a lot of ground. This would be a perfectly good course all by itself, this lecture. But the good news is there are pretty pictures involved. So it's going to be a picturesque view of what the universe is made of, as far as what we can see. And then in later lectures, we're going to take the evidence from what we see and plug it into our theoretical notions to try to derive notions of what it actually is made of. So, even though the universe looks the same everywhere, there is one thing that makes it not quite that simple, which is that it's getting bigger as a function of time. What that means is that different objects in the universe used to be closer together. In the future, they're going to be further away. So we're going to tell you the story of how this was discovered, and then in the next lecture, what it means in a deep down level. It's very often that you will hear people trying to explain to you the concept of the expanding universe by appealing to really bad analogies. So as a professional cosmologist, this gets my dander up a little bit when people use these analogies with the best of intentions to explain the idea of the expanding universe. For example, they will have a balloon, and they will take a balloon, and they will put little dots on it, and they will blow up the balloon. And as the balloon gets bigger, you see the dots moving away from each other, and they go, aha, the dots moving away from each other are just like galaxies moving away from each other in the expanding universe. And that's correct in a sense, but you have to admit that when you see the balloon expanding, there's an inside to the balloon and an outside to the balloon. But our universe is not like that. So the balloon analogy only works if you look at the dots on the balloon and then imagine there is no such thing as the inside or the outside of the balloon. It's possible to make that leap of imagination, but it's harder than just understanding what's going on in the first place. Similarly, the other analogy that is very famously used is raisin bread. You start with a lump of raisin bread dough with raisins inside, you put it in the oven, and the bread expands, as perhaps you know. The raisins move away from each other and people go, there you go, it's like the expanding universe. But again, you get a misconception from this analogy, and that's because the raisin bread has an edge, it has a crust. The raisin bread is also moving into something when it expands inside your oven. The universe, as far as we know, is all there is. When we say it's expanding, it's not getting bigger into some pre-existing space. What we mean is that the individual objects inside the universe are getting further apart. Now, how is that possible? How can you have the individual objects in the universe get further apart even though it's not expanding into anything? So that's going to be the next lecture where we explain how Einstein's theory of general relativity allows the space in between the objects to grow. Space-time itself is dynamical and can expand. So I'm not going to use any analogies whatsoever. I think the best way of understanding the expanding universe is to actually visualize the universe, the actual universe that we're in. Because once you start conceptualizing it as some object inside something else, you get the false impression. As far as we know, our universe is all there is. There might be something outside, but we don't need to appeal to anything outside to understand what's going on. So let's just think about the universe. Let's think of going outside, standing outside on a clear night where there are no clouds, and looking at the night sky. Furthermore, let's imagine that you have perfect vision. So what I mean is not only that you can see things that are very faint, and you can see things that are very small, you can also see in all the wavelengths of the electromagnetic spectrum. In other words, you can see visible light, you can see radio waves, you can see X-rays. I'm giving you perfect vision. You're standing outside, you're looking at the universe, and you're saying, what do I see? Well, there's some things that are obvious. You see the sun and the moon. They're fairly nearby as far as cosmology is concerned. You also see stars. You see stars and you see planets orbiting around the sun. These are all well and good, but the thing that I want to focus on, that we would see if we were standing outside on a clear night, is something called the Milky Way. The Milky Way is a band of what looks like a cloud, what looks like milky whiteness stretching from one edge of the horizon to the other edge, overhead. And if you were able to look closely enough at it, you would realize that this thing that looks like a cloud is in fact made of stars. The Milky Way is a huge collection of stars, and we can look at it better in the real world. We can have a satellite. So in fact, NASA's COBE satellite, which is short for Cosmic Background Explorer, took an image of the Milky Way. Here's an actual image of the Milky Way taken from a satellite. It looks like a galaxy. It looks like a picture of a galaxy that you would see taken by any other telescope. It looks like it's taken from the outside. But we really live inside the Milky Way. The trick is the Milky Way is a disk. So you imagine a disk of stars all orbiting around each other, and we're located near one edge. So when we look inside, we see the center of the Milky Way is a concentration of stars. You see less stars in other directions, very few in the opposite direction. We're embedded in a plate-shaped collection of stars, and that is called the Milky Way galaxy. The Milky Way has about 100 billion stars in it. You don't know the exact number. Some stars are too faint for us to see, but 100 billion is a good order of magnitude estimate. Any such collection of stars is called a galaxy. The important point here is that these stars are not fixed, sitting there in space. They're orbiting each other. So there's a pull due to gravity from one star to every other star, and this entire collection of 100 billion stars is orbiting under their mutual gravitational field. So you could ask, is that the whole universe? Would it be possible to imagine a universe in which you had the Milky Way, a collection of 100 billion stars, some planets inside and some clouds of gas and so forth, and nothing outside, emptiness stretching forever and ever? Well, it's a very plausible idea. It's certainly worth taking seriously if you didn't know any better. And 100 years ago, that was the leading understanding of what the universe was like. This was the so-called island universe idea, that we lived in the Milky Way. The Milky Way was a collection of stars orbiting around each other, but there wasn't anything else. There wasn't anything outside the Milky Way. However, astronomers did know there were different kinds of things inside the Milky Way. When we look at the sky with our perfect vision, we see not only stars, which are always points, no matter how much you zoom in on a star. There's no telescope on Earth that ever expands it to look like a disk. It always looks like a point. But there were other objects that were not stars that you could definitely see did have an extent. These were called nebulae, nebulae plural of nebula. These look like fuzzy little patches in your telescope or on your photographic plate. So 100 years ago, this was the hot topic in astrophysics. What are these fuzzy little patches called nebulae? Here's a picture of the Orion Nebula. This is a picture that they couldn't have 100 years ago. We have much better telescopes today. You see, it's a very colorful, very rich collection of gas and dust. In fact, we know today that the Orion Nebula is a star-forming region. It's a huge cloud of gas that is gradually collapsing under its mutual gravitational force, and it will splinter off eventually to form individual stars. So that is one kind of nebula that exists. The Orion Nebula is right here in the Milky Way. There are many, many other nebulae just like it here in the Milky Way. Here's another picture of a nebula. This is called the Andromeda Nebula. To a telescope, 100 years ago, the Andromeda Nebula looks like a fuzzy patch, just like the Orion Nebula looks like. All these different nebulae that you could see 100 years ago had different shapes and sizes, but they were all fuzzy little patches. We knew they weren't stars, but we didn't know what they were. The truth is that the Andromeda Nebula is actually the Andromeda Galaxy. The Andromeda Nebula is its own collection of 100 billion stars orbiting under their mutual gravitational attraction. In other words, the Andromeda Nebula is just like the Milky Way. It is not inside the Milky Way. It's a separate collection well outside the Milky Way. We do not live in an island universe. We live in a universe filled with galaxies just like ours. So how do we know that? This is something that was first figured out by Edwin Hubble, who was a remarkable figure in his own right. It took Hubble quite a while to find himself as an academic. He grew up more famed for his athletic prowess than anything else. He was a high school track champion. He played for the University of Chicago basketball team when they won the National Basketball Championship, which they're not likely to do ever again. He was a Rhodes Scholar, went to Oxford, and studied law for a while, studied Spanish for a while, came back to the United States and actually worked as a high school basketball coach as well as a lawyer. Eventually, he realized his true calling was astronomy, so he got a degree, a PhD, in astronomy, and he went to California. The reason he went to California was to go to the Mount Wilson Observatory, which at the time was the world's leading astronomical observatory. They had just built a huge new telescope, the 100-inch Hooker telescope. 100 inches refers to the diameter of the mirror that was used to collect light. So you had a large mirror collecting light. You could see distant stars and distant galaxies with a better perception than you ever had before. So what Hubble did was to look at things that look like nebulae, little fuzzy patches, and number one, he resolved them into individual stars. So not everywhere, not at the centers, but at the edges of these nebulae, you could see that it was not just gas and dust. There were individual stars there, and there were a lot of them. That was certainly suggestive that these were not, in fact, just clouds of gas here in our galaxy. They were individual collections all by themselves. But you still couldn't be sure. It could just be that there were a few stars, that they were still relatively close and inside our galaxy. How do you know how big the Andromeda Galaxy is? You can't count all of the 100 billion stars. The answer is that Hubble was able to measure the distance to the Andromeda Nebula. He was able to figure out that the distance between us and Andromeda was such that, given the stars he observed, there must be billions and billions, as Carl Sagan would say, stars in that nebula. So how do you do that? Use a technique called standard candles. This is a very simple idea. Imagine that you have some object, and it's a certain distance away from you, like a candle, and you can see that it has a certain brightness. Then someone takes that object and they move it twice as far away. If you're in a dark room and all you see is the object getting further away, once it's twice as far away, it will seem dimmer to you. In fact, if it's twice as far away, it will only have 1/4 the brightness. There's an inverse square law. So as something gets further and further away, it looks dimmer. That makes perfect sense to us. The problem is, if you don't know how bright it was to begin with, you can't figure out how far away it is. So the difference between a candle and a standard candle is a standard candle is something whose intrinsic brightness is known. If you know how bright the thing would be if it were a fixed distance from you, and you know how bright it appears to you, you can work out how far away it must be to make that distance and that brightness make sense. So one of the major projects in astrophysics and cosmology, 100 years ago and still today, is to find standard candles and measure distances to things. As you're standing outside just looking at stars in the universe, you see all these stars, but you have no idea off the top of your head how far away they are. So what you do is you build up something called the cosmic distance ladder, and the most important technique is the use of standard candles. For Hubble, the standard candles he used were something called Cepheid variable stars. This is a type of star that pulsates. It gets bigger and smaller, and the standard candleness is not absolute. So Cepheid variables are not all exactly the same brightness, but they also don't all have exactly the same period of oscillation. In 1908, Henrietta Leavitt, an astronomer at Harvard, although women were not allowed to be called astronomers at the time, but she was an astronomer and she was at Harvard, and she noticed one of the crucial discoveries in all of astronomy, which is that there is a relationship between how bright the Cepheid variable is and its period of pulsation. So even though you don't know just from the fact that it is a Cepheid variable how bright it is, if you measure its period, then suddenly you do know how bright it is. So Henrietta Leavitt calibrated this relationship. She taught us, if you see a certain period, then it must be a certain brightness. Hubble went to his Hooker telescope, the 100-inch telescope at Mount Wilson, and he discovered Cepheid variable stars in the Andromeda Galaxy, as well as in other galaxies. And he noticed that these variable stars, given their periods, were much, much dimmer than the Cepheid variable stars in our galaxy. So he could work out how far away they were, and he realized that Andromeda was a galaxy all by itself, comparable in size to the Milky Way. In fact, we now know that we live in a local group of galaxies. The Milky Way is one of them, and the Andromeda Galaxy is the other big one, and we have many smaller galaxies that are satellites of these two. So Hubble established the first important fact about our universe, namely that it is big. In fact, we now know that in our observable universe, there are about 100 billion galaxies that we can observe. That's a convenient number. In fact, 100 billion is basically the only number you need to remember in terms of how big the universe is. There are about 100 billion stars in a typical galaxy. There are about 100 billion galaxies in the observable universe. The age of the universe is about 14 billion years, but that works out to very close to 100 billion dog years, if one ordinary human year is 7 dog years. So 100 billion is the scale of the universe using different units. Here is a picture from what is now known as the Hubble Space Telescope, named after Hubble, which is an orbiting satellite that was built by NASA. This particular picture is called the Hubble Ultra Deep Field. All they did was take the telescope, pointed at a blank direction in the sky, a direction where they didn't know anything was there, but they let it sit there and collect a large number of photons over a large period of time, and then, so to speak, they developed the image. What you see in this picture is a lot of galaxies. Almost every little dot in that picture is a galaxy all by itself, with literally billions of stars in it. So Edwin Hubble was the one to figure out that the universe is big, that not only do we have a galaxy with 100 billion stars, but that galaxy is not unique, it's one of 100 billion galaxies spread throughout the universe. So that's a nice picture of what the universe is made of. It's not an island. It's not just the Milky Way galaxy surrounded by nothingness. There's a collection of galaxies spread out. But don't get complacent, because the universe is not just staying there, it's getting bigger. This is the second important fact about the universe. After the fact that it's big, the second fact is that it's getting bigger, and this is also discovered by Hubble. He was not the first to get on to some idea like this. In fact, an astronomer called Vesto Slipher noticed that galaxies that he observed tended to be redshifted in the light that came from them. So what does that mean? When we have atoms giving off light, it is very frequently the case that the light it gives off in a certain kind of atom is always at the same frequency. The wavelength that you have of light will be determined by what kind of atom is giving it off. So if you look at an atom and it's giving off this light, you know what wavelength the light should have. But when he looked at distant galaxies, he noticed that all the wavelengths of light that he was observing were stretched. We're going to go into this more detail later, but basically you go from a short wavelength blue photon, particle of light, to a longer wavelength red photon, and Slipher found that this was happening over and over again in the galaxies he observed. Now the phenomenon of a shift in the wavelength of light was well known. It's the Doppler effect. The Doppler effect is the thing that makes the pitch of noise change as an object goes by you. You start with something that is coming toward you, and it goes by, and a very high-pitched noise that you hear when it's coming toward you will convert to a low-pitched noise as it goes away. That's just because the waves of sound coming toward you are compressed, going away from you are elongated, are lengthened. So you get a blue shift when something's coming toward you, something is squeezed to shorter wavelengths. When something goes away from you, you get a red shift. So Slipher looked at all these galaxies. He said they're all redshifted. In other words, all of these galaxies seem to be moving away from us. So that's halfway to saying the universe is expanding. All the galaxies are moving away from us. But it's not quite all the way. It was Hubble who figured out the rest of the story, because it was Hubble who knew how to measure the distances to galaxies. So Hubble went, and with his collaborator, Milton Humason, compared the distances to galaxies that he had measured to the redshifts that Slipher had measured, and he found a fascinating result, that the apparent velocity that the galaxy would have to have moving away from you to explain its redshift was strongly correlated with the distance. The correlation is that the further away an object is, the faster it's moving away from you. So that is what you need to be able to say the universe is expanding. So instead of a bunch of galaxies exploding away in some primeval explosion, if we imagine that the whole universe is just getting bigger, if the space in between all the galaxies is expanding, then you will see close-by galaxies move away gradually. Far-away galaxies will be zooming away from you at a huge speed, because there's more space in between you to do the expanding. That was what Hubble discovered. He didn't call it that, though. This plot that you're looking at right now is Hubble's original plot of the data. He plotted the distance on the x-axis and the velocity on the y-axis, and it kind of looks like a noisy plot. It kind of looks like there's a scattering of points there, but Hubble was a genius. So he drew a straight line through it, and he turned out to be correct. The next plot is a much more modern version. It looks like the points are much more closely aligned with a straight line, which is true, but also the size over which you're now measuring distances and velocities has grown enormously. So you really do have very strong evidence that the universe is expanding. If you look at this plot and think about what it's telling you, you realize that even though the universe is expanding, Even though all the galaxies are moving away from us, it is not that we are in the center of the universe. We see nearby galaxies moving away, further away galaxies moving away even faster. But if you were that middle galaxy, if you were the galaxy in between, you would see us moving away in one direction and the distant galaxy moving away in the other direction. In other words, in this collection, every galaxy sees every other galaxy moving away from it, and the further they are, the faster they're moving away. There's no special point to this. Every galaxy is moving away from every other galaxy. It's the whole universe that is expanding all at once. So Hubble had an equation, and I'm actually going to show you this equation. Occasionally during this course we will see equations. We're not going to use them. I just think it's important not just to mention that equations exist, but to actually look at them and show what they're saying. So here's an equation: velocity equals h times the distance. H is a constant, a number, which we now call Hubble's constant. So this equation is just telling us that the velocity of a distant galaxy is some number, some fixed number once and for all, times the distance to that galaxy. So the further away the galaxy is, the faster it's moving away. Now I said once and for all, and what I mean is, in our universe today, every galaxy obeys this law, but the Hubble constant is really better called the Hubble parameter, because it's telling you how fast the universe is expanding. In the past, the universe was expanding much more quickly. So what we call the Hubble constant was a much bigger number in the early universe. It turns out that measuring the actual value of the Hubble constant is much harder than you might think. It's been something that cosmologists and astronomers have been struggling with for decades, but we think that we finally pinned it down. Wendy Friedman of Carnegie Observatories and her collaborators have measured the value of the Hubble constant, and the answer they got is 72 kilometers per second per megaparsec. So what does that mean? Kilometers per second per megaparsec is telling you the Hubble constant converts from distances to velocities. So 72 kilometers per second per megaparsec means that one galaxy, 1 megaparsec away, will be seen to be moving 72 kilometers per second away from you. If it's 2 megaparsecs away, it'll be moving 144 kilometers per second away from you. So what is a megaparsec? A megaparsec is 1,000,000 parsecs. A parsec is about 3 light years. In other words, a parsec is about 30 trillion kilometers. It's a very big distance. A megaparsec is a typical distance to a fairly nearby galaxy. So this number, the Hubble constant, 72 kilometers per second per megaparsec, measured by Wendy Friedman in the 1990s, is basically setting the scale for the universe. It sets the time that it takes the universe to expand. It sets the distances to different galaxies. So the fact that we figured out what this number is a big step forward in our understanding of the scale and the size of the universe. Now that we know that distant galaxies have this relationship, the Hubble law, their apparent velocities that you observe are proportional to their distances, it becomes much easier to map out the universe. Measuring distances to galaxies is hard. You can't find Cepheid variables in very distant galaxies, they're just too far away. But measuring redshifts is easy. So we can use the redshifts, the velocity measurements, as a stand-in for distances. If you know that the bigger the velocity, the further something away is. So this plot is a picture of where galaxies are in the universe, created by a survey called the Sloan Digital Sky Survey. We live at the center of this picture, and you see 2 cones moving in either direction. That's just because there was a northern hemisphere survey and a southern hemisphere survey. It cost money to collect every one of these data points, so they didn't observe the whole sky, they just observed parts of it. Every one of those little dots, which are almost too small to be seen in this plot, represents an individual galaxy. This is hundreds of thousands of galaxies spread throughout the universe. So you see 2 important lessons. One is that the universe is basically the same everywhere. There's no dramatic difference between one side of the sky and the other, or from place to place in that universe. If you took a big sphere of space that was sufficiently big, megaparsecs across, and took the number of galaxies in that sphere, and then took another sphere just as big in a completely different part of the universe, you would get basically the same answer. This is the crucial simplifying feature that makes it possible to study our universe in a systematic way. It's more or less the same. The second feature is that it's not exactly the same. When you look closely at this image, you see there is structure there. There are little holes where there are almost no galaxies. There are concentrations where there are more galaxies. Those are clusters and superclusters of galaxies. The evolution of the universe at early times from being almost perfectly smooth to being the slightly non-smooth, lumpy distribution that you see in this picture is a fascinating story that cosmologists are just beginning to unravel right now. The universe is pretty smooth on large scales right now. In the past, it was even smoother, and so we're trying to understand how we got there from here. So that's the picture that we have of the universe. It's quite a nice picture, but it's also quite provocative. To put it into context, we'll say the basics again. The universe is big. That is to say, it's not just one compact collection of stars. It spreads out as far as we can see. It's getting bigger. The space in between galaxies is growing. That manifests itself as the idea that every galaxy you see appears to be moving away from us, and Hubble's law tells us that the further away it is, the faster it appears to be receding. It is smooth on large scales, so we can treat the universe locally in basically the same way that we treat the universe far away. The same average density, the same number of galaxies, the same basic properties of the universe should apply here as somewhere very far away. And then we can start thinking about what that means. If the universe is getting bigger now, that means that in the past it was smaller. We can imagine taking the current state of the universe and asking, what was it like? Where did we come from? So if things were smaller, they were denser, they were closer together, there were more things in every cubic light year or every cubic megaparsec. And if that keeps going, if you can extrapolate that back, then things became very densely packed. They're very hot. As things bump together, they heat up. And if you keep going, you get to the Big Bang. You get to a point where the density is infinitely large, where everything is on top of everything else. That would be a naive extrapolation from the fact that we're expanding now. Go backwards, and what do you find? You find that everything is on top of everything else. It's perfectly reasonable to say, we shouldn't be so naive. There might be some change in the velocity of expansion. Change in the expansion rate. Maybe it started out not expanding. Maybe the universe was static and only slowly began to grow. So what we need is a theory. It's not enough to make the observations right now that the universe is expanding. We need a theoretical understanding of how it should expand in the presence of different kinds of stuff. So that theoretical understanding is given to us by Einstein's theory of general relativity. So general relativity was invented about 1915. The expansion of the universe was finally discovered by Hubble in 1929. So physicists had about 14 years to play around to try to figure out what should happen according to general relativity. And what they figured out will be the subject of the next lecture and the one after that, is that the expansion of the universe depends on what is inside. So, in other words, after this picture of what the universe is like, we're drawn back to the questions of dark matter and dark energy. We have claimed in the introduction lecture that 95% of the universe is dark matter and dark energy. Dark matter is some kind of particle that is heavy, massive, slowly moving, but has a local gravitational field. Dark energy is something that is smoothly spread out and something that persists. It doesn't go away as the universe expands. So given those ingredients, given the theoretical understanding of space and time that general relativity provides, we can ask the question, what did the universe look like in the past? Was there a Big Bang? What will happen to the universe in the future? Will it expand forever, or will it contract? Now, these are not trivial questions. When Einstein invented general relativity, someone started saying very quickly thereafter that if space-time were expanding, according to this theory, there should be something called the redshift. There should be a lengthening of the wavelength of photons. But not everyone believed it. Einstein himself was very skeptical about this effect. So when Hubble found that the universe was expanding, found that distant galaxies obeyed this relationship, they had a velocity that was proportional to their distance, he never spoke about that phenomenon in terms of general relativity. Hubble never said, I discovered the expansion of the universe that people working with general relativity had predicted. He always talked about just what he observed. He was a really good observer. He didn't want to make predictions or judgments on the basis of theories. So he never said, I've discovered the expansion of the universe. What he said was, I've discovered that distant galaxies are moving at a velocity that is proportional to their distance. He also kept saying, and I deserve the Nobel Prize for discovering this, but he never won the Nobel Prize. In Hubble's time, the Nobel Prize for Physics was not considered something that astronomers should ever get. So he died without winning the Nobel Prize. After he died, they changed the rules, and now astronomers are winning the Nobel Prize all the time, which is as it should be. So in the next lecture, we're going to talk about Einstein and his general theory of relativity, for which he also never won the Nobel Prize. But it forms the basis for our understanding of space and time and will let us make sense of this picture of an expanding universe.